The big question that we want to answer for the rest of this semester is what finite abelian groups exist? Right? If you hand me a finite number of elements, how many different ways, different meaning fundamentally different, under the surface different, how many different ways are there for me to make a group out of that number of elements, that finite number of elements that you give me, when that group is abelian? The question, if we strike the word abelian from the sentence, is really a hard question. It's a question that mathematics didn't even know the answer to until I was in grad school, around 2004 or 2005. The question of what finite groups may exist in general. That question, surprisingly, has an answer, but it's a very complicated answer. What so-called Atlas of Finite Simple Groups was published when I was in graduate school, and purported to be, here is a list of all of the building blocks for finite groups that might exist. Then you can take those building blocks and put them together in a variety of ways. But that question was answered only in 2004. And so it's much too challenging for us in the course of our first semester looking at group theory. But the abelian question we can answer. So what I want to do is give you a sneak preview as to what the answer is and how the answer works, and then we'll backtrack and talk about what are the pieces that we're going to need to develop ourselves in order to justify that answer. So here's the idea. The answer to this question is really what we call the fundamental theorem of finite abelian groups. So it seems fitting that the fundamental theorem should be the thing that we build toward this semester. And it's an answer to the question, how can we list all possible finite abelian groups of a given order, n? And the theorem says something akin to the statement that every finite abelian group is a direct product of Z mod p's. These are groups that are cyclic groups, and their order is a prime number or possibly a prime power of a prime number. So that's the main idea. So here's an example of what the fundamental theorem is going to allow us to do. It's going to allow us to answer a question like this one. List all abelian groups of order 120. So if you give me 120 elements, how many different ways can I make an abelian group out of those 120 elements? And so if it's true that the prime power order cyclic groups are somehow the building blocks of our answer, then we want to figure out what are the raw materials that I'm going to have to work with if I have 120 elements to make a group out of. So what are the prime building blocks of the number 120? Well, how do we figure that out usually? We'll build a factor tree and figure out what are the prime factors. So we do the factor tree, we find out that the prime factorization of 120 includes 3 powers of the prime 2, 1 power of the prime 3, and 1 power of the prime 5. So what that is going to suggest to me from the point of view of this fundamental theorem is that I really kind of have these 5 little building blocks. I've got 3 building blocks that might be groups that are somehow related to the cyclic group of order 2. I've got 1 building block that looks like the cyclic group of order 3, and 1 building block that looks like the cyclic group of order 5. So I have these 5 different blocks that I can try to build a group out of. And one way to build a group out of these 5 smaller groups is just to kind of string them all together in a long horizontal line like this, using this mysterious operation that I'm writing as a plus sign with a circle around it. This operation is called a direct product, so it appears in the statement of our theorem. It is also the subject of our standard number 8. That's the next thing we're going to do, because it's that operation that allows us to build bigger, more complex groups from simpler pieces. Right? It's a way to stick 2 groups together and make a bigger group. So I could just stick these 5 things together, and this is an example of an abelian group of order 120. But, and here's what else the fundamental theorem is going to allow us to do. I can take these 3 red blocks, these 3 Z2s, and I could stack them in a variety of other ways. For example, I could take 2 of those Z2 groups and sort of smush them together to make, instead of 2 separate groups of order 2, I could smush these together somehow to make a group of order 4, a cyclic group of order 4. And as we will be able to persuade ourselves, the group Z4 and the direct product of Z2 with itself are not isomorphic to one another. They are fundamentally different. And this is how the fundamental differences in our answers that the fundamental theorem are going to give us work. We've got one of these pieces that's now a cyclic group, the other piece is not cyclic, and therefore these 2 groups in the squares are not isomorphic, right? Because we know that cyclicity is preserved under isomorphism. So we know that this group that I build by stacking these on top of one another is going to give me fundamentally a different group than the one that I had down here on the bottom. So Z4, Z2, Z3, Z5 is an example of a different algebraic structure that still is going to have 120 elements in it and be abelian. Right? Well, if it's good for stacking 2 blocks on top of one another, shouldn't it also be good to try to stack 3 blocks on top of one another? 3 factors of this Z mod 2 stacked on top of one another. And if I smush these together, I'm going to get a cyclic group of order 8. So a cyclic group of order 8 and order 3 and order 5 direct product together is going to, again, give me a fundamentally different structure, because this Z8 is a cyclic group, and this Z4 direct product Z2 will not be a cyclic group. So not isomorphic. But what's great about the fundamental theorem is it tells us that by the time I'm done stacking my blocks, that's the end of the story. Okay? There are no other different, fundamentally different structures for an abelian group of order 120 other than the 3 ways of stacking these 3 red blocks on top of one another. Now you might ask, well, why couldn't I have stacked a red block on top of a blue block? Why couldn't I combine together a order 2 and an order 3 factor? What's going to happen if I try to do that? And the answer to that comes in trying to simplify, trying to find out if there's a better way to write down the structures that we see in these groups. And without giving too much away, one of the most important things we're going to learn in section 8, when we start it later in this week, is that if I have cyclic groups whose orders are relatively prime to one another, as 8, 3, and 5 are, then it turns out I can stack the red on top of the blue on top of the green, and I end up with a single cyclic factor whose order is the product of those relatively prime factors. So when I stack Z8, Z3, and Z5 all together, I get a single cyclic group whose order is 120. And this is a group that we probably would have already been able to guess, right? List all abelian groups of order 120. Well, every cyclic group is abelian. So if I make a cyclic group of order 120, then that will qualify. That's got to be one of my examples. And indeed, here it is. Z120 is really the same thing as this group that I listed here. But what about in our second example? If I'm stacking 2 of these blocks, I could take this Z4 and combine it with one of the other relatively prime factors, like Z3, and maybe another relatively prime factor, Z5. But what I cannot do is I can't try and stack this group of 2 blocks on top of this block. I can't combine the Z4 and the Z2 factors because those are not relatively prime. So any combinations of relatively prime factors in these direct products, I can recombine back into a larger cyclic group. For example, the 2, 3, and 5. If I stack this block, this block, this block, those, because 2, 3, and 5 are relatively prime, are going to be isomorphic to a single cyclic factor of order 30. But then this cyclic factor of order 4 is going to be sitting out on its own. I can't combine this one with that one because 4 and 30 are not relatively prime. I could also have made the choice to stack these 2 on top of this one and that one and leave a single Z2 out in the cold. Right? 4, 3, and 5, after all, are relatively prime. And I would get Z2 direct product Z60. And so then our last structure, the only things I can combine are a 2, a 3, and a 5, right? Because all these other 2s, well, they're the same as this 2, really. And so this 2, 3, and 5 combines together to give me a 30. And so in simplified form, here are the 3 different structures that we can have for an abelian group of order 120. It could be cyclic, so it could be a cyclic group of order 120. Or it could have factors 4 and 30 or 2 and 60, and those 2 actually give me the same group up to isomorphism. Or it could have the factors 2, 2, and 30, which is giving me a different one altogether. So there's 3 possibilities, and here are the ways to write them down. So really the question about how to find what all abelian groups, finite abelian groups, can exist is really a question about, first of all, breaking down the number 120. Right? So we had to somehow break it apart, figure out what are the options for breaking it apart, and then try and reduce that down to its most essential building blocks, which turn out to be these cyclic groups of either prime order, Z2, Z3, Z5, or power of a prime order. When I stack one of these blocks on top of another one of the same color, I get something that has a prime power, 2 to the 2nd power, 2 to the 3rd power. Right? So those prime power order cyclic groups are the building blocks of all finite abelian groups. So what do we have to understand in order to see this big picture? Because at this point, if you believe the fundamental theorem, now you can answer any question like this just by doing a prime factorization and stacking up some blocks and simplifying. So there's a part of me that says maybe that's the first thing we should do this week. Just bring in a bunch of blocks, give you some large composite numbers, and say, give me an exhaustive list of all the finite abelian groups of this order. But let me give you an overview of how the rest of the topics break down. The first one that I was planning to start this week is the question about building. How do we build structure? How can I make new groups from old? If I have old groups that are easy to understand, how do I smush them together to form more complex new groups that have more interesting structure? And that's this idea of a direct product structure. So the very first thing we're going to do is be able to take 2 groups, G and H, that might have nothing to do with one another, and smush them together into what we call an external direct product of those groups. just by creating a group whose elements are ordered pairs, where the first element in the pair comes from the first group, the second element in the pair comes from the second group. What we do is we get a new group called the external direct product, G direct product H. And so that's where this little symbol is going to come from. It's just a way of, kind of like we have the x-axis and the y-axis, and we smush them together to form the xy plane. Right? That is exactly the construction that we're doing here. So that's, on the one hand, how to take and put together groups to build them up. The analogous question is, if you just hand me a group, is there a way that I can somehow break it apart to discover an internal product structure that it might have? If you hand me a group, can I find out whether that group really is a product of two things? How do I break it into smaller pieces? For example, could I find a subgroup, K, and a subgroup, L, such that if I were to break this group apart into K and L, that K and L would multiply, they would take the direct product of them back together to give me G. If I can, then my group has an internal times table structure. We can arrange its elements so that it makes its own multiplication table, which would be really cool. That would be a really powerful thing to understand about a group. We would call that an internal direct product. But our ability to do that relies on our ability to divide up groups in general. If you hand me a group of 120 elements, can I somehow split it up into 10 columns and 12 rows, or 5 columns and 24 rows, or 60 columns and 2 rows, right? What are the different ways to do that? How can I divide up a group? And that's topic number 7. How do we divide structure? If you give me a group, how can I find out what simpler pieces might be able to fit together to give me that larger group? So let's take a group like D5, the dihedral group of the pentagon. It's got 10 elements. And if you just hand me that group, I have sort of a sack full of 10 symmetries. Not a whole lot of structure there, right? But what can help us to make order out of this chaos is to think about subgroups. Subgroups are going to help me to organize elements. One example of a subgroup of D5 is that cyclic subgroup generated by R, right? All the powers of R, and then R to the 5th wraps back around to the identity. That's a subgroup of D5. And so maybe I can make a little diagram of my group in which that subgroup forms the first row. Well, then what would the second row be? Well, an element I didn't have here was the reflection, T, which is its own inverse, so T squared wraps back around to the identity. But E and T together make another subgroup. So this row here is a subgroup. This column here is also a subgroup. And it would be nice if this group had an internal times table structure, so that the remaining 4 elements could all be seen as a product of T with one of the elements from this subgroup. And indeed, that is how we get the other elements in D5. So D5's elements make its own little times table, multiply something from this subgroup by something from this subgroup, and in a unique fashion, that forms all the other elements of our group. And this is really nice. It gives me really 2 different ways of looking at this group. I can look at it by rows, or I can look at it by columns. If I look at it by rows, this first row is a subgroup, and the second row is obtained from the first row just by multiplying each one of these elements on the left by T, right? R is here, T times R. R cubed, T times R cubed. Right? Every element on the second row is T times an element from the first row. And so we call that set of elements T times K. If K is this subgroup, T times K is going to be this second row. Now, T times K is not going to be a subgroup. Give me one good reason why T times K is not a subgroup. But the most obvious reason, I think, why this T, the second row, is not a subgroup is the identity element's not there. Right? So it doesn't satisfy the identity property. And yet, it bears a striking resemblance to a subgroup. Right? It is nothing more than a shifted subgroup. I just took this subgroup and I moved it to a different spot in the group by multiplying all of its entries on the left by T. We call that a left coset. So coset is nothing more than what we get when we take a subgroup and we move it somewhere else in the group by multiplying it by an element. In this case, I'm multiplying it on the left, so we call it a left coset, by the element T. Similarly, I could have taken this subgroup, E and T, call that subgroup L, and I can multiply it, let's say I multiply it on the right by R. If I do that, then E is going to turn into R, T is going to turn into TR, and I get what we're going to call a right coset of that subgroup. The right coset that I get by multiplying it by R. So the second column here is just a right coset of the first column, which is a subgroup. The third column would be a right coset as well. It would be LR squared, LR cubed, LR to the 4th. And so looking at this in 2 different ways gives us 2 fashions in which we can divide up D5. I can divide it up into 2 rows, where the first row is a subgroup and the second row is a coset of that subgroup. Or I can divide it into 5 columns, where the first column is a subgroup and the other 4 columns are the other cosets of that subgroup. But it turns out one of these ways of looking at the group is better than the others. So the question is going to be, and this is where we're going to wrap up for today, is there going to be a sense in which I can treat the rows of this table as elements in and of themselves as part of a group? If I were to take this whole set and make it a single element, and then this whole set and make it another single element, would those two elements form a group under the operation of D5? Similarly with the columns. If I took each of these 5 columns and made it a separate element, could those 5 elements form a group with the operation that's inherited from D5? And the answer in the case of the rows is yes. The answer in the case of the columns is no. And the reason for that is that there's a difference in the kinds of subgroups that we have. That K is going to have a property that L does not. A property that we're going to call normality. K is a normal subgroup. L is not a normal subgroup. And so, as you might expect, it's going to be the normal subgroups that are actually going to be the building blocks for our groups. And the non-normal subgroups, well, they're uglier. We're not going to be able to do as much with them. And so topics number 9 and 10 are all going to be about the search, the hunt for normal subgroups. Figure out what they are, why they matter, and how do we find them, most importantly. If you give me a group, how do I find these normal subgroup building blocks?